Here's another example. Car of mass m slides across a patch of ice at speed v with its brakes locked. Brakes locked meaning the wheels are not spinning, they're just skidding. So that means that we're dealing with kinetic friction, not static. It hits the dry pavement and skids to a stop in a distance d. Coefficient of kinetic friction between tires and the road is mu. So we can always say, of course, work done by the net force is equal to change in kinetic energy. In this case, with what we're given, what makes the most sense is to write this work done by the net force as net force times distance, technically dot product, of course, but in this case, the net force is going to be in the direction opposite the motion. The net force is caused by friction. So it's 1/2 m v final squared minus v naught squared, and we know that v final is 0 this time because we're coming to a rest. The net force is caused by friction, which is equal to mu times normal force. In this case, in the vertical direction, the only things happening would be normal and gravity. So the normal force in this case would be equal to mg, and that force is going to be directed opposite the direction of the displacement of the car, which means that the work is then going to be negative. It would be mu mgd times cosine of 180, which is -1. And then that's equal to 1/2 minus mass times v naught squared. And we notice, what? Look at that, mass goes bye-bye. So if the mass of the car changes, distance doesn't change. It doesn't actually matter because we've got a mass on both sides of our equation. Now, looking at the relationship between speed and distance, looking at our equation, we can see that distance is proportional to v naught squared, so doubling the velocity would then quadruple the distance, which incidentally is why it's important one reason that it's important not to drive too fast, because as the faster you drive, the more energy you have and the harder it is for your car to come to a stop. And that's a quadratic relationship, not a linear one. So driving at 40 kilometers per hour versus 20 isn't twice as dangerous, it's 4 times as dangerous. Now here's another fun problem. And you know, when I say fun, that means difficult. So we got mass m1 resting on a frictionless inclined plane, angled at theta above the horizontal. String connects the mass, runs over the top of a pulley. That is attached to hanging mass m2. This is a modified Atwood's machine. The system is released from rest. We want to know what the total kinetic energy is when the masses have traveled a distance d. Well, we know work done by the net force is equal to a change in kinetic energy. And we know work done by the net force is equal to some of the forces dotted with our displacement. Excuse me. In this case, the tricky part is figuring out what is the sum of all the forces. So we need to do Newton. Forces acting on M2. We've got gravitation. We've got tension. On M1, tension, gravitation, normal force, frictionless plane, so we don't need to worry about friction. And since it's frictionless, that means that the normal will just cancel out with the component of gravity, and we don't need to be concerned with that. So in the x direction, we have m1, we've got t minus m1g sine theta. It's going to be equal to, well, m1a, but that doesn't matter because all we care about for finding work is the net force. We don't actually care about the acceleration side of Newton's second law. On m2, as always, we need to make sure we have our signs appropriately set up. So going up the plane, positive, that means that m2 going down is positive. And adding them together, we can see that the net force acting on the system is m2g minus m1g sine theta. So that's what we can then plug in for the net force, m2g minus m1g sine theta. Delta x, well, it's traveled distance d. It's equal to change in kinetic energy. So 1/2 v final squared minus v naught squared. Well, in this case, what is moving? Well, both masses are moving, so for the mass here, we'll have to use m1 plus m2 times v squared. Now it starts from rest, so v naught is 0, so that's v final squared. Oh, actually, this is asking about the system's total kinetic energy, so we don't actually care about what we could also figure out the velocity using that, but it just asks for k, so we're done. Kinetic energy is equal to d times m2g minus m1g sine theta. If it asks for velocity, we'd then divide this out and then square root solve for the speed of the system. And here's another example. Mass m is sliding along a frictionless surface at speed v when it encounters a spring that is initially relaxed. The spring compresses a distance x. Determine its spring constant. Well, we know work net is equal to change in kinetic energy. In this case, if the spring compresses a distance x, that means when it compresses that distance, the mass momentarily comes to rest before being sprung back. So we can say that v final is 0, and we know the work done by a spring is going to be 1/2 k x naught squared minus 1/2 k x final squared. We figured that out last class. And the spring is initially relaxed, so that means x naught is 0. So then we're left with minus 1/2 kx final squared equals minus 1/2 mv naught squared. So the negatives cancel out and the 1/2s cancel out. So then we have kx final squared equals 1/2 mv naught squared. And the problem calls our initial speed v and the final compression distance x. So plugging that in, I'm sorry, this half canceled out. E equals mv squared over x squared. I believe your homework has something like that, where you use numbers instead of doing it algebraically.